Hello again. Welcome to the last module of the webinar on nanoscale phase change memory devices. In this module, we're going to discuss about several reliability factors of the PCM devices. We have already discussed about the high resistance state, the low resistance state, and the intermediate states of PCM. And we have also discussed the electrical pulses that are used for resetting and setting the pulse. Now, how do we get the intermediate states? In order to achieve the intermediate states, sometimes we may need to start from the LRS and we may gradually reset the cell so that we can stop somewhere at the intermediate states. Say, for example, if we start from the 10 to the power 3 or 1 kilo ohm, and if we want to go up to 10 to the power 5 or which is 100 kilo ohm, then instead of applying one single high amplitude reset pulse, we can apply some gradually increasing smaller reset pulses so that can increase the resistance gradually. And as soon as we reach up to our desired resistance level, we can stop pulsing. So that is one popular way to go to the intermediate states from the LRS. But we often start from the HRS toward the intermediate states. So when we go from the HRS toward the intermediate states, we often apply smaller partial set pulses. So the idea is again the same. Instead of applying one large set pulse, we apply several smaller set pulses to gradually set the high resistance state toward the intermediate state. So pulsing in this nature is called partial resetting or partial setting of the cells, and we can reach toward these intermediate states from LRS or from HRS. Now the problem is that doing these partial set or partial reset operations can be tricky because in these programming there are some variability in the reached programmed state. The obtained programmed state is often different than the target programmed state. So our program resistance can be different than the target program resistance, and these variations can be obtained from cell to cell. Say for example, if this is an array where we have various cells, we may see that in order to reach to the same target resistance of 100 kilo ohm, when we start from the same initial resistance of 1 kilo ohm, and even if we apply the same sets of gradually increasing partial reset pulses, we may see that different cells are reaching to slightly different intermediate states. They are not all of 100 kilo ohm. So this is called the programming variability. And when we have this programming variability from cell to cell, we call this as the cell to cell programming variations. Now, when we have these cell to cell programming variations, we not only obtain this because of the process variations, where because of the process related steps, the sizes of these cells can be slightly different, which may require different pulses to reach to the different sets of pulses to reach to the equal resistance level. But on top of the process variation, we also have inherent programming variability in the PCM programming operations. So this programming variability is a physical source of variations which is unrelated to the process variation. So when we melt a cell and amorphize, this melting and quenching process itself has some variations inherent to it. Similarly, when we crystallize a cell from HRS to LRS, this crystallization includes the nucleation of small crystalline islands and their growths. So there are variations in the location of this popping up of the crystalline islands, and there is also variations in their growth. Hence, these amorphization and crystalline, both programming has its inherent physical variation, which we are terming here as the programming variability, which is an added term to the process variation. Now, because of this physical variation, we also observe this programming variability from the cycle to cycle operation on the same cell. So when we go from LRS to HRS, again come back to LRS, while going back to HRS again, we may see that in the two cycles of operation, we are not reaching to the exact same HRS. Also, we are not reaching to the exact same LRS even though we are applying the same set or reset pulses. So these are termed as the programming variability, and in usual memory operations, we try to minimize these variations as much as we can. Now there is another problem in the multi-level cell operations, that is the phase change memory experiences drift of resistance which is spontaneous and thermally activated, and this drift of resistance is mostly and severely experienced in the amorphous phase. Now the intermediate states also experience to some extent of this resistance drift, but the amorphous phase experience it to the most. The HCP phase does not experience any resistance drift, and the FCC experience very slight of it. But in the amorphous phase, we have the power law behavior, and we also can define some drift exponent to define how much drift we observe. Now this is a thermally activated process, so as we increase the temperature, this drift can be modified. Now this is an example of how the data retention is observed at various temperature of the PCM cell. So these measurements were done at various ambient temperature. The top black one was done at the room temperature, where you see that the amorphous resistance is increasing with the parallel behavior, and after reaching to a maximum it would start decreasing. So this increase of the resistance is known as the resistance drift, which is an upward change of resistance. And again, I would remind you from the previous slide, we said that this is a spontaneous process and a thermally activated process, but this going down nature of this resistance is known as the crystallization process. Now these can be modified when we go to higher ambient temperature. So at the room temperature, we can go up to 10 years of retention time in the PCM. So the retention time is defined in this way: how long it takes for the cell to retain the stored data. So when we store this cell as the high resistance state, we want this cell to stay at this high resistance state for a long time. So that is called the retention time. But this cell spontaneously is going to a much higher resistance and then going back to a lower resistance spontaneously, even at room temperature. So it takes about 10 years. So the retention time of PCM is about 10 years. Now, depending on the different material, this can be modified as well. And also when we go to higher temperature, the retention time can be in the order of seconds, as you can see here. Now the drift exponent that we define is a marker of how steep the resistance drift would be. For the HCP, we see almost no resistance drift. That is why the HCP crystalline phase is also known as the stable crystalline state. In the FCC state, we have very slight resistance drift, which is upward, and in the amorphous phase we see quite severe resistance drift, which is also in the upward direction. Now the data loss trend from the amorphous to the crystalline is would not always follow the same path. So if we cycle the same cell again and again, starting from the same resistance value, and if we anneal to accelerate the data loss process within a few thousandths of second, we would see that this data loss does not follow the exact same path. So the reason behind that is when we have these crystallizations in the amorphous region, there are some crystalline islands that would nucleated, and after these nucleations, these nucleated crystalline islands would grow in size. For example, here you see that one island is growing, and as other islands are popping up, they are all growing together and merging together. Now, this nucleation of different islands can be at different locations and at different times, even when we cycle the same cell during the crystallization of the different cycles. So because of these variations in their locations and the timing of their popping up, we can have different decrease of resistance for over time, and that is why we have different trajectory for the spontaneous data loss trend in the PCM. Now again we are bringing back the drift exponent. The drift exponent can be slightly lower for the intermediate states, and if we consider the intermediate states, we would see that the higher intermediate states would have larger drift exponent, and the lower resistance intermediate states would have lower drift exponents. So we can explain that in the higher resistance intermediate states, we can have a larger proportion of the amorphous phase, and hence we see the larger drift exponents. And in the smaller or lower resistance intermediate states, we can observe smaller drift exponent because of the smaller proportion of the amorphous phase. I'd like to conclude this module with some key points. First of all, phase change memory or PCM is a fast, dense, non-volatile memory technology. Most commonly used phase change material is the germanium antimony telluride with the 2-to-5 composition. The resistance of the phase change material can be switched to the high and low resistance states with appropriate electrical pulses that are called reset and set pulses. And the PCM is a storage class memory which can bridge the speed gap between the existing memory and storage technologies. I'd like to thank you for your attention in all my modules. Finally, I'd like to acknowledge my institution, North-South University, for supporting me. I'd also like to thank University of Connecticut of USA, from where I did my master's and PhD. My works were done in the Nanoelectronics Laboratory of UConn, and the devices that you saw in this presentation were fabricated at the IBM T.J. Watson Research Center. These works are funded by the U.S. Air Force Office of Scientific Research and the National Science Foundation. Finally, I'd like to thank the IEEE Women in Engineering of the Dhaka University section, and I'd like to thank you for your kind attention on all my modules. If you are interested for my other publications, please check my Google Scholar profile. Thank you very much.